Good day, Math 30-1s. Today we begin a new unit called Permutations, Combinations, and the Binomial Theorem. Today's first topic is 11.1, which refers to something called permutations, or perms as we call for short. The large idea today is to develop the idea behind something called the fundamental counting principle, as well as discovering there's a formula, NPR, a strange notation that we'll investigate further. So our first investigate is to talk about getting dressed in the morning, and you lay out your clothing in three different sort of options. You've got three shirts, you've got two pairs of pants, and you've got two pairs of shoes. So you could wear a red shirt, khaki pants, and orange shoes, and that would be considered one outfit or arrangement. Big question is, how many different arrangements could you wear? Well, if we try to visually organize this, we can make a tree diagram to talk about option 1 being your shirts, option 2 being your pants, and option 3 being your shoes. If we start with a red shirt, we could say that there are two options, and we could branch off from your red shirt to talk about your khaki pants or your white pants. We could similarly say the same thing for the green shirt, talk about your khaki pants or white pants. For blue shirt, khaki, white. Now, you could be wearing a red shirt and khakis, and a yellow pair of shoes, or an orange pair of shoes. Similarly, from your red shirt, white pants, be wearing yellow and orange. Yellow and orange. Yellow and orange. Continuing with our yellow and orange a few more times gives us a whole bunch of maps or branches in this visual organizer. So we could be wearing, if we sort of put these together, red shirt, khakis, yellow shoes. We could be wearing red shirt, khakis, orange shoes, and so on. Now, I won't write all these down because it would take a bit of time, but how many different arrangements could you wear is the question. And if we did write them all out, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different options. 12. So in examining potentially a faster way to create this total number of arrangements, often people will recognize that what's happening is you've got three choices that is ultimately branching off into two choices for each. So 3 times 2 gives us 6 options. All 6 of those options are introduced to another 2 possibilities, and the 6 times the 2 makes a 12. So there's actually 3 options for option 1. There's 2 choices for option 2, and 2 choices for option 3. And if you do multiply those together, it does give us the correct number of options, which is 12. So a few people might recognize that a potentially faster way of creating the total number of arrangements is to multiply the number of, we'll say, choices together. And this is essentially saying you've got choices for A, choices for B, choices for C, multiply them together, and you got your total number of options. This idea of counting brings us to something called the fundamental counting principle, which essentially says, like we did before, if you have A ways to perform one task, or A choices, and B ways to perform another task, or choice, then there is A times B ways to do both, or to piece them together. So we can examine a few different examples today, and I'll start with one that is fairly logical. Imagine you have a simple luggage lock, and you were trying to get into it, and you forgot your combination. There are 3 choices for numbers on these 3 different tumblers that you can see. So each of these tumblers in this example has the option of 0 through 9, 0 through 9, and 0 through 9. How many different codes are possible if you forgot and needed to potentially attempt them all? Well, the fundamental counting principle says that you've got 3 different choices. Tumbler A has 0 through 9 as possible options, 0 through 9, and 0 through 9 as the options for the other 2. This gives us 1 through 9 plus the 0 10 choices for every tumbler. And if you do multiply them together, you would end up with 1,000 possible, I'm going to use the word permutations. That's another way to say arrangements. So 1,000 different ways to create codes on this lock. Now that should make sense because you've got combination 000, 001, 002, all the way up to 999, which does add up to 1,000. Now this question is a little bit simple, but it does take into account a nice visualization of the fundamental counting principle. Let's try an example with a little bit more complexity that says, what if we could not repeat a digit? So if the first number was a 7, it can't be used for the remaining tumblers. So this still is 3 different tumblers or choices, but in your 0 to 9 options in the front with a 10, that brings us to 0 through 9 as options, but take away the first number. I'm just going to write a little condition under each line to help clarify. Now I don't know what that first number was. Could have been a 3, could have been a 2, could have been a 7, but I don't care. All I know is I have one less choice. Similarly, you've got 0 through 9 as options. Can't use the first number, can't use the second number, and we're down to 8 choices. Piecing that together gives us 10 by 9 by 8, or 720 different possible arrangements or permutations. So you can see that it's less because we're not allowed to repeat, but this simple idea of the fundamental counting principle makes complex tasks simple. So we'll attempt one that's quite a bit more difficult in a lock combination question. This one says a new lock needs 3 entries. 3 tumblers. Each tumbler, though, is made up of a 2-digit odd number. So you could have a number here like 13, 27, and 91. Numbers can repeat. How many options are there? If I were to ask you how many 2-digit odd numbers are there, we might not know off the top of our head. So let's do a little math on the side to say how many 2-digit odd numbers are there. Now, I guess we should clarify, by a 2-digit odd number, does that imply that 05 is a 2-digit odd number? Or is 05 technically a 5 and it's a 1-digit number? For the purposes of this question, let's consider 05 a 1-digit number, and so 1 through 9 are our only choices. But there is a bit of a debate about what would work. What defines an odd number? Well, you would need to end in a 1, a 3, a 5, a 7, or a 9, which means, according to the fundamental counting principle, we've got 1, 2, 3, 4, 5 options for the last space, 9 options for the first space, which means there are 45 2-digit odd numbers if we were to count 11, 13, 15, 17, and so on up to 99. So there are 45 possible options for the first entry, 45 for the second, and 45 for the third. And if you multiply those together, they should give us the total number of 2-digit odd number entries for a lock with 3 of these spaces. So multiply those together, and you would end up with 91,125 possible lock permutations. Now, this is a bit of a challenging one, which you would probably see towards the end of an assignment, but it still gets you thinking about what's possible. At the very bottom, we have a try one asking about license plates. So a license plate is currently made up of 3 letters followed by 4 numbers. Now, this is a new format that does not include custom plates, but if there are no restrictions, so no restrictions on what letters or numbers could be used, how many license plates are possible in Alberta? So if we know that we need letter, 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 number, 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 we've got 26 letters in the alphabet for each of those spots. And again, repetition is okay. 10, 10, 10, 10 options for each. We could have, multiply those all together, 175,760,000 possible license plates. Now, typical questions might say, If the old system only had 3 numbers, how many license plates were added under the new system? So questions can be a little bit more complex built on this premise, but we can tackle questions about license plates, postal codes, area codes, and phone numbers. Anything that has these options that we can piece together. So let's delve into something that's a little bit different, things where we can't copy and paste options. So in an example that involves students, what if we had 5 students that were assigned for a class next semester, and I was making a seating plan, and I have only 5 seats. So 5 seats, 5 students, how many seating plans could I make? Well, imagine that you're in phys ed, you're in gym class, and you are captain picking a team. You're looking up at 5 people, and you've got 5 positions for your team, 5 seats. How many options are there for that first seat? You look up and you see 5 people. Now we can't copy and paste a person, so there isn't that person that is filling all of those positions or seats. So we're left with 4 people to select from, and then 3, and then 2, and then 1, and this descending number from 5 to 1 gives us a 5, 4, 3, 2, 1, 120 possible seating plans. Now, 5, 4, 3, 2, 1 is kind of interesting because it's just descending and also multiplying. It became so important that factorial notation was introduced, which is a concise representation of multiplying consecutive descending natural numbers. So whether it's a 5 factorial or a 10 factorial, we're simply saying take that number and multiply it by every number that follows descending from it to 1. Now, as a variable, this is an n factorial, and so we would have an n minus 1, so take away 1, take away 2, take away 3, all the way down until 1. Okay. So we can't have negatives, we can't have decimals, but we stop at 1. So in order to understand factorial notation, we're going to examine a couple interesting cases. If I were to say determine 8 factorial, most people would grab their calculator and say 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that is great, but it became so important that people realized, there might be a need for 8 people, 8 desks to do this more concisely. On the graphing calculator, factorial notation was introduced. If you press 8 followed by the math button on the left, the math button, and go to the right where it says PRB, down to number 4 which says factorial, not exclamation mark. In math, that's factorial. And if you can make it say 8 factorial, it's going to manually calculate 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or 40,320. So, as questions may get a little bit more complex, we have examples like 6 factorial over 5 factorial, and before you type in your calculator 6, 5, 4, 3, 2, 1, or the 6 factorial button, there is a little bit of logic that can make this a bit more quick. 6 factorial is 6, and then 5, and then 4, and 3, and 2, and 1. And so instead of writing all those, let's just stop at 5 and say that it keeps going, 5 factorial. Well, why? Because we actually have a 5 factorial on the bottom. And that 5 factorial on the top and the 5 factorial on the bottom could cancel out. This in fact leaves us with 6. So instead of saying 6 factorial is 720, 5 factorial is 120, and dividing them, we can see it's just 6. Similarly, if we were to do that with 10 factorial over 8 factorial, we can say 10, 9, 8, and so on, all divided by 8, and so on, cancel out the 8 factorials, and say 10 times 9 is 90. Much more quick than 10 factorial divided by 8 factorial. Now the reason for doing this canceling is because sometimes questions that have too large of a number pose a problem. If you were to try 100 factorial divided by 99 factorial, we see a bit of an issue. So 100 factorial, and this is the only number I'll type in, gives us an overflow error, which means there's too many digits for the calculator to handle in 100 times 99 times 98 and so on. So it doesn't mean there's no answer, it just means we need to be creative. 100 times 99 and so on divided by 99 and so on gives us 100. So understand that when dealing with large numbers like 100 factorial, the calculator is very limited. So with this idea of factorial notation, there are variables. So under investigate for which of the values of n are the following expressions defined? It is important to note that just like 2 to the power of 0 has a value of 1, there is a special value that needs to be remembered or noted, and 0 factorial has a value of 1. And this will be needed for the math to make sense going forward. So 0 factorial is 1, which means we've got a potential cutoff of n plus 8 to the factorial. So if we were to plug a negative 8 into this, we would have a negative 8 plus 8, which makes a 0 factorial, which would be okay. Try a number like negative 9, and this would not work. Negative 9 plus 8 makes a negative 1 factorial, which doesn't really work. Negative 1 descending would become a negative 1, negative 2, negative 3, negative 4, and so on, and that doesn't really work. So negative 8 is our cutoff. So we can say for what values of are n defined, n has to be greater than or equal to negative 8, and n must be an element of the integers because we're not allowed to have decimals or fractions. For letter B, we've got n minus 5 factorial over an n plus 4 factorial, and most people would recognize it's probably going to be something about a 5 or a negative 4. There is one statement we can make that governs letter B. So what if we were to say, negative 4? Negative 4 plus 4 makes a 0 on the bottom. 0 factorial is 1, so that would be okay. But if we try negative 4 on the top, negative 4 minus 5 makes a negative 9 factorial, and that's no good. The cutoff is, in fact, 5 minus 5. 5 plus 4. 5 is a cutoff that works. So we can say that n must be greater than or equal to 5, and n must be an element of, now because it's not negative, I technically don't have to use integer. I could say whole or natural number to simply say it doesn't really need to be negative, so natural numbers works just as good. So with a little bit of notation with variables out of the way, we're going to examine a little bit of canceling. So algebraic factorials could cancel just like the 100 factorial over the 99 factorial 1 did, but it can be a little bit, we'll say, trickier. So a question asks us to simplify or make more concise n plus 1 factorial over n minus 1 factorial. We take the larger number, which in this case is the one that's adding 1, and we're going to descend n plus 1 factorial into an n plus 1, and then 1 less is n, so take 1 away, n, take another 1 away, n minus 1, and I could keep going and say n minus 2, n minus 3, n minus 4, but I am going to stop there because I already have an n minus 1 factorial on the bottom. And just like we canceled in the example in the previous page, we can cancel the n minus 1 factorials, which leave us with an n plus 1 times an n. And we could multiply those together, but the intent is that we're simplifying or making more concise. So I'll stop there, but we could go further. This is needed for number 2, which asks to now solve the equation for n. So somehow there's a perfect value for n which would make everything equal 90. Well, I'm going to descend that top n into an n minus 1, n minus 2, and so on, so that I can cancel out that n minus 2 factorial, which leaves us with no factorial. Simply an n times an n minus 1, and I'll write that as an n squared minus n, which equals 90. Conveniently, that 90 can subtract over and factor into an n minus 10, n plus 9, which equals 0, giving us two potential answers. N is 10 and negative 9. One of these is extraneous because if you take the negative 9 and return it back into the original question, we can't deal with a negative 9 factorial or a negative 9 minus 2, negative 11 factorial, so we get to say it doesn't help. But 10 factorial and 10 minus 2 factorial both are possible, so a 10 does work for n. Now, with a little bit of the variable algebraic questions out of the way, let's examine a few contexts with this fundamental counting principle that can become a little bit more intense. Investigate 5 says there are 3 prizes, first, second, and third, available to be won. Let's call this a race. A class of 5 students is offered a chance to win. They are in this race. How many different ways could the prizes be awarded? So a person could win first or second or third, or they could sort of not win at all. So we're dealing with 3 prizes, and we're going to go back to the fundamental counting principle and say, just like you're in phys ed or gym class selecting 5 people for a team, we've now only got 3 prizes or 3 seats or 3 positions with 5 students. So the first seat or spot or position has 5 choices. The next spot has only 4, and the next spot has only 3 as we lose people with each choice. Multiply this together, and you'd end up with 20 times 3, 60 possible ways for these prizes to be won. Now, with this type of logic, the challenge is that I can't use the factorial button anymore because 5, 4, 3 is missing the 2 and the 1. So a little bit of creativity might tell us that, technically, if I were to continue a times 2, 1, and then make sure mathematically it's sound by dividing by a 2 and a 1, I technically should be able to write 5 factorial divided by 2 factorial, and then at least I can use that button press on my calculator. Now, that might be a little bit of an intense bit to remember. So what we actually have built is this idea of keeping factorials and creating a formula for that. So I'll come back to the 5 factorial over 2 factorial as we examine a new formula that makes our lives quite a bit simpler. So the notation for a situation above, where we have objects and selecting from those objects, takes the form of NPR, which represents the number of permutations or arrangements, the number of ways to select something or someone, that can be made from a set of n different objects where only r of them are used. So in the context of this question, NPR has 5 people, and we are only selecting 3 of them. Now the formula has an n factorial over an n minus r factorial. 5 is the n, so we have a 5 factorial divided by n minus r factorial, which is 5 factorial over 2 factorial, which, if you kind of compare, has the same value. So this formula becomes a very, very powerful tool in saying I've got this many objects and this is how many I'm going to select. So as we go to try 3, we've got an example that talks a little bit about songs. So imagine you have 10 tracks and you're going to go for a run, requiring maybe only 6. And for the context of this question, let's assume that order is pretty important. So maybe you are wanting to start with a bit of a pump-up song and you're wanting some noise, and then maybe you're going to end with some Michael Bublé or something where it's kind of a cool down. So order might be important. So determine how many 6-track playlists could be made from the 10 downloads using the correct notation. So if you were to use the fundamental counting principle directly, you would say you've got 1, 2, 3, 4, 5, 6 songs to select, or 6 options. But you've actually got 10 to select from. So you've actually got 10 choices, and then 9 once one is selected, otherwise you're playing all the same song, and then 8 and 7, 6, 5, and if you multiply those all together, it is a pretty big number. Now, if we're using the formula, you might say I've got 10 tracks, and I'm going to select 6 of them. Now, the good thing is that we've got a formula which makes this a little bit simpler, 10 factorial over 10 minus 6 factorial, which results in a big number divided by a 4 factorial. Now the good news is that there's actually a button press on the calculator for this as well. So if we press the 10 and then math over to PRB, we're going to select the option that says NPR. So I pressed the 10 first, I went to my NPR option, and we're going to select 6. This tells us we've got 151,200 different playlists that could be made of 6 songs from a choice of 10. So however you attempt this question, whether you're using the formula, whether you're using the button press, or whether you're using the fundamental counting principle, all the different ways result in a 151,200, which gives us the element of choice. So far we've talked a little bit about how the fundamental counting principle turns into factorials, and how selecting only a smaller amount of objects can be used with a formula. And now we're going to talk a little bit about solving permutations where conditions are involved. So conditions. And as soon as we start talking about conditions, it's a little bit challenging to use the formula because the formula can't take into account little detail changes. So whenever we see conditions, we're going to go back to the fundamental counting principle, which we'll just consider as those lines. So in this next example, we've got 5 people seated on a bench, or maybe 5 friends going to a movie. How many ways can these 5 friends be seated in those 5 seats if person E has to be in the middle? So for this seat, there's only one option. For the remaining seats, it could be anyone. So it could be person A, B, C, D, which gives us 4 options. It could be person A, B, C, D, except for that first one's already seated, so there's only 3 choices. And then similarly, we're descending down to 1, which gives us 12 times 2, 24 possible ways to seat these 5 friends if E is in the middle. What if person A and B needed to be together? So we've still got 5 seats, but the challenge with this is that 2 of these lines are sort of stuck together. It actually makes sense to consider 2 of those seats one object. I'm going to represent 2 seats as one object and the other remaining seats as their own object. So what's actually happening here is we've got this group of 2 seats, these 2 people, that could be somewhere in the middle, or they could be on the other end. They could swap out with any of these other circles, but really there's only 4 objects. So we can consider this a 4, 3, 2, 1 rearrangement of 4 objects. And most people would feel pretty comfortable to say it's 4, 3, 2, 1 or 4 factorial. But